In today's video, we're going to be talking about the mathematics of physics. After watching this video, you should be able to calculate the average of a group of numbers, understand why we have error in measurements, be able to calculate uncertainty, use trig functions, and then gain an understanding of sign convention used in physics. All right, so a lot of things to talk about today. Should be an exciting video. Let's get right to it. The average, I'm going to make the assumption that you guys know how to calculate average already. So I'm going to fly through this really quickly. To find the average of a set of data, all you have to do is add all the numbers up and then divide by how many numbers there are. So for instance, let's say you have 6 different velocities, and I've listed them right here. Okay, so here they all are, and this is all in meters per second. Okay, so you have 6 different velocities. I'm wondering, what is the average velocity of these numbers? Okay, so you'd add all these up and divide by 6 because there's 6 different numbers. And if you do that work in your calculator, you should get an average of 0.325 meters per second. Now, if you were to do this to the correct number of sig figs, there's only only 2 sig figs in all of these numbers, and so the average really, I guess, would be 0.33 meters per second. Okay, so that's basically what the average is. Okay, we're going to need to be able to do that though in some of the other topics that we're going to talk about in this lesson. So let's talk a little bit about errors. Okay, we all make mistakes, and in science the same is true. There's 2 types of errors. The first type I want to talk about is random errors, and these basically are errors that are uncontrollable variations in just measurements. Okay, and so some sources of random errors include the observer being less than perfect. Okay, so you as the scientist, if you will make mistakes as you measure things. Okay, that is bound to happen, and so you yourself are actually a source of error, you as the observer. The readability of the equipment. Okay, I was involved in a science camp this past summer, and they had electronic balances that would only read to the ones place in the grams. Okay, so like it would only be like 5 grams, 6 grams. It had no decimal point, and so it wasn't very good equipment. It was actually very cheap electronic balances, and so that can be a problem. Is the ability of the equipment to give you a good answer. And then reaction time in general. There's a ton of labs that we're going to do in this class that involve you using a stopwatch. Well, what if you're a little delayed pushing the start button on the stopwatch? Or what if you're a little slow pushing the stop button on the stopwatch? Those are all things that can cause for errors and your numbers to not be quite correct. The way to combat random errors basically is by doing multiple trials. And so that's why the old number 3, at least 3 trials, is kind of the benchmark. And really, if you can do more than that, great. I mean, like in the real scientific community, they run experiments over and over and over again to try to minimize the amount of error that is being found in an experiment. And so you can actually get good data that you can use to know what's happening. The second type of error is called systematic error. And a systematic error is when the measurement is bigger or smaller than the true value. Okay, so it's always off by the same amount. So the true value is something that I typically will give you, and a systematic error is something that basically the device itself is not providing a correct measurement. Okay, so a good example of this would be like not reading from 0. And what does that mean? Well, let's say you have a ruler, and I can't tell you how many times I see students do this, and I wish they wouldn't even make rulers this way. But let's say the 0 starts right here, okay, and then here's 1 and 2 and so forth. Students will say they want to measure a pencil, and again, I'm not a real good artist, but here's a little pencil. They started at the end of the ruler where the 0 isn't even there. Really, the pencil needs to be at the 0 mark. And so they're always measuring a little short, if you will, on every piece of every item that they're trying to measure. And that is a systematic error. And the shame is that finding the average doesn't help. Okay, if you always measure incorrectly, well, you're just averaging a bunch of incorrect measurements. So that is not a way to help it. So not reading from zero. So zeroing your electronic balances, if you're putting like a weigh boat on it and getting a zero on it, is another example of systematic error. Okay, so there's this thing called uncertainty, and basically in every measurement there is some uncertainty. And you may say to yourself, well, what causes this uncertainty? The measuring device itself can cause some uncertainty. Your experimental procedure will cause some uncertainty. Okay, so maybe your experiment isn't run quite correctly. Or the nature of the measurement. Okay, so like let's say you're trying to measure the speed of light. That's kind of a tough task, and so that's a lot harder to say measure than maybe like the acceleration due to gravity on Earth. Okay, that's a lot easier to figure out than trying to measure the speed of light. Okay, so that also will cause uncertainty. So let's take a look at one of the types of uncertainty, and this type of uncertainty is dealing with analog devices. An analog device is basically something that does not have numbers displayed with like an LED screen or numbers that kind of flash at you per se. So an example would be like a watch that has a minute hand and a second hand and an hour hand and all that good stuff. Or for instance, this ruler down here is considered an analog device. Okay, it doesn't have numbers and stuff that pop up. It's just, there it is. The way you calculate the uncertainty of an analog device is you take the smallest scale division and divide it by 2. Okay, so we can see on this ruler, we have millimeters. So here's 1 millimeter right here. And basically, we can take that smallest scale division, so here's 1, here's 2, and 3, and this would be like 0.1, 0.2, 0.3, and so forth. We can take that and we can divide it by 2. So I had the example here, we took 0.1 divided by 2, and so we have an uncertainty of plus or minus 0.05 for our answer. So let's just, for example, let's say I have a pencil, and here's my pencil. And let's say I measure the length of this pencil, and that's not a very straight line, but let's say it's somewhere like around here. We could say that that measurement is 4.6 centimeters plus or minus 0.05. That would be my uncertainty right here, plus or minus 0.05. So that's how you do that with analog devices. With digital devices, these are things that do actually like flash at you. So, you know, like an electronic balance, a stopwatch, you name it, a digital thermometer, those types of things would be all considered digital devices. And basically the uncertainty is plus or minus the smallest unit shown. And sometimes that's referred to as the least count. Okay, so for example, let's say you're using a electronic balance and you get a measurement of 20.06 grams. Okay, there is an uncertainty with that balance of plus or minus 0.01. Okay, plus or minus 0.01, and that would be the uncertainty. It's the least unit shown, and then you just say plus or minus how much that is. So 0.01 for that. If you are taking repeated measurements, and hopefully if you are doing an experiment, you would be taking repeated measurements, you would want to calculate, or here's an example. Let's say I'm calculating the height of a table, and I measure it 5 times, and here are my results of measuring it 5 times. First thing you want to do is you want to find the average value. And if you add all those numbers up and divide by 5, I got an average value of 1,562 millimeters. That's supposed to be millimeters. All right. Then you calculate the uncertainty. And the way to calculate the uncertainty is you take the maximum value minus the minimum value and you divide that by 2. And if you take, it looks like the maximum value is 1567, 7, that's supposed to be a 7, minus, let's see here, 1555, and you divide that by 2, I get plus or minus 6 millimeters about. And that would be my uncertainty. So next to this measurement that I found for my average, I would put plus or minus 6 millimeters. Okay, and that would be considered my uncertainty. So there's some rules for uncertainty, and there's only 2 of them. Uncertainty must only have 1 significant digit. So let's say you calculate the uncertainty of something and it's 6.3 0.3762. I'm just making this up, okay? If that's the number you get, you can only have one significant digit, so it would actually stop at the 6. Okay, that would be it. You'd be plus or minus 6. Okay, you wouldn't put all this gobbledygook at the end. Okay, so only one significant digit. The second rule is that the last decimal place of a measurement must be the same as the decimal place of the uncertainty. Well, what does that mean? Well, basically, if I have 20.06 grams, kind of going back to my electronic balance example, my uncertainty cannot go past the hundredths place. Okay, so let's say I calculate the uncertainty of this measurement, and I find it to be 0.0376 or something like that, okay? I can only have my uncertainty go this far to the hundredths place. Why? Because this number here is to the hundredths place. I can't have it go all the way to, the thousandths or anything like that. It can only go to the same decimal place as my measurement. And so those are the two cardinal rules of calculating uncertainty. Beyond just saying, plus or minus 6 millimeters, there's really 3 ways that you can state uncertainty. This one that I have right here as an example, that's called the absolute uncertainty. Absolute uncertainty. And so that would be plus or minus 6 millimeters. The fractional uncertainty is just basically taking your absolute uncertainty and dividing it by your number. And so I kind of have a typo here. This really should say 1562. So my apologies there. 1562. So 6 divided by 1562, I'm guessing is still probably pretty close to 0.004. That would be my fractional uncertainty. And my percentage uncertainty, again, this is a little bit of a typo here. It should really say 1562. And as is this should say 6 divided by 1562. So I'm really sorry, this slide's kind of messed up. But 6 divided by 1562 should be about 0.04%. Okay, 0.4%. Okay, and those are just 3 ways to state uncertainty: absolute uncertainty, fractional uncertainty, and then percentage. All right, let's take a break from uncertainty and talk a little bit about some trig functions that you guys will need to definitely be able to use, especially in first semester physics. And there's a mnemonic device that I like to use, and this is nothing I created, in terms of remembering the 3 trig functions that you need to be aware of, and that's sine, cosine, and tangent. Okay, and that, if you notice, I have this SOHCAHTOA across the top, and the first letter of this mnemonic device is what I just wrote down in each of these words. So is the S stands for sine, ka, the C stands for cosine, and toa, T stands for tangent. Okay, and this is the first part of dealing with this SOHCAHTOA and the formulas associated with them. Then the O in the SO stands for opposite, and the H stands for hypotenuse. All right, so sine equals the opposite over the hypotenuse. And you may say opposite over, what is the opposite over, and that kind of thing. I'll do with it in just a second, so let me go through these other guys, and I'll make a picture and we can talk about it. Cosine, is the A stands for adjacent, and the H stands for hypotenuse. And then tangent, the O stands for, again, opposite, and the A stands for adjacent. Okay, so I'm going to just quickly draw a triangle here, a right triangle. That doesn't look very right triangle-ish, but there it is. And I'm going to put a little symbol here that stands for theta, and theta is standing for this angle that's being created by these 2 lines. Okay, so when I'm saying the sine is the opposite over the hypotenuse, it's the opposite from this angle. So the opposite here would be, like, we'll label this line here y. Okay, that would be the opposite of this angle right here. And then the hypotenuse is just the long side of a triangle. So this would be the hypotenuse over here. And I'm going to give that actually a number right now. I'm going to call that 8. Okay. Cosine stands for the adjacent. The adjacent to what? To this angle. And so the adjacent is here, and I'm going to label that x. Okay, so this is the adjacent over the hypotenuse, which would be 8 in this case. And the tangent is opposite over adjacent. So opposite would be y over x, if you will. Okay, so we're going to do some practice real quickly with this. I'm going to say that theta equals 25 degrees. So let's say I know this angle and I know the hypotenuse. Can I figure out what y would be in terms of a numerical value? And the answer is I can. All I'm going to do is I'm going to take the sine of 25 degrees is equal to, now what is sine? Opposite, so it's y, over the hypotenuse, which is 8. Okay, so I have one unknown and two knowns. Can I solve for y? Absolutely. Basically, in the end, what you're going to do is you're going to cross multiply sine 25 times 8, and if you do that, I get y equals about 3.4. Okay, and you can check on your calculator to make sure you're able to do this, because it's important that you are able to actually do these trig functions. Okay, so that's an example dealing with sine. Let's change pen colors just to, I don't know, brighten things up. The cosine is adjacent over hypotenuse. So let me draw a triangle. Hopefully I can do a better job of it. Oh yeah, that is so much better. Here's theta, here's y, here's x. I'll call this 8 again, and I'm going to still have theta equals 25 degrees. Okay, so now what about this x component? Can I figure out what x is? Well, I can. The cosine of 25 degrees is equal to adjacent, which is x, over the hypotenuse, which is 8. Okay? And basically, if you cross multiply and you take cosine 25 times 8, you should get x equals 7.3. And that would be my answer. Okay? So this is an example of using cosine. Okay? Let's do an example using tangent, and I'll change pen colors one more time just because it's so much fun. So again, I'll draw a triangle here. I'm not certain that's going to come out real well. Let me change colors one more time to magenta. Here is theta, and we're going to say theta this time equals 40 degrees. And let's say I know y, but I know this, and I don't know y, and this is 6. Okay, can I figure out y? And the answer is I can, because tangent equals opposite over adjacent. Okay, so I would put tangent 40 degrees equals opposite, which is y, over adjacent, which is 6. And basically, in the end, if you just cross multiply 6 times the tangent of 40, you would get y equals about 5. Okay, we will do this a lot. We'll practice more in class, but I wanted to just expose you to some of the math that you're going to need to be able to have and use for first semester physics. And this is one biggie that you need to be able to do, is the SOHCAHTOA stuff with trig. So if you want to spend some time practicing or looking at these problems a little more, be my guest, but onward and upward. The last thing, and this is pretty simple, at least I think anyway, is dealing with basically sign conventions. And sign conventions are basically an arbitrary thing. They are completely up to you in terms of how you want to do it. But once you pick some sign conventions, I recommend sticking with it. The typical sign conventions are basically based off of, like, if I were to make a graph, okay? If I move to the right, I'm going in the positive direction. If I move to the left, I'm going in the negative direction. If I go up, I'm going in the positive direction, and if I go down, I'm going in the negative direction. Okay, and so where this is used is it's the directional piece when we start talking about like velocity or acceleration, or even sometimes forces. We'll put a plus or a minus sign in front of our answer to indicate a directional type of piece. One thing that we're going to deal a lot with is, let's say I'm standing on a cliff. Here I am standing on a cliff, and I have a rock in my hand, and I'm going to drop this rock. We know that the rock's going to fall down to the ground. Why? Well, gravity's going to pull it down, right? Well, because we're saying it's going down, typical sign convention is going to make gravity almost always be negative, okay? And it's not so much that it's a negative values per se, like in math. It's more so of a directional piece indicating that it's going down. It's moving downwards, okay? Or let's say I have a car that's accelerating to the right, and I am not a good artist, but it's supposed to be a car. Let's say I have a car that's accelerating to the right, okay? So it's speeding up, heading in the right direction. Typically, you're going to have this be plus, okay? So let's say it's accelerating at 2.5 meters per second squared, and it would be moving right, okay? So accelerating to the right at 2.5 meters per second squared. So these are the types of sign conventions that I'm talking about. Now, let's say you want to just, really be different, and you want to call down plus and up negative and left positive and right negative, like completely switch the sign conventions. You can do that. Everything will work out just fine. You'll get the right answers. But typically, I'm probably going to be using this type of sign convention because it's much more standard, much more common to use. Up is plus, down is negative, left is negative, right is positive. All right, so that's what I'm talking about when we talk about sign conventions. And again, we'll deal with this a lot more as we move through class, but this is just an example of some of the sign conventions. That takes care of this video. I'll see you guys next time.